Okay, here we are talking a little bit about ceramics, and this is for engineering studies HSC students. And this is your syllabus here, and you can see down over this way. Ceramics, you need to know about the structure-property relationships, their application to civil structures, and discuss a bit about glass, cement and bricks. And know how to choose what sort of materials for what sort of purposes, particularly in the use of civil structures, which is a unit that we're now doing, and investigate the relationships of the properties of the material to their use in civil structures. So that's what we're going to do, and I think we'll do it in about, 2 or 3 sessions, 10 minutes or so each, if all things go to plan. Alright, so let's start. Firstly, it might be a good idea to talk about what is a ceramic. And ceramics come in lots of different shapes and sizes. This is an igneous rock, naturally occurring rock. It's actually a paperweight. Ceramics occur as stones, as we discovered, we spoke about earlier. They can occur as glasses in different shapes and forms. They won't look quite like that, but they'll be dark, black, obsidian-like structures. And they can occur in clay form, so in a putty sort of a clay form. And they can occur in several different kinds of ways. So it's not all immediately obvious to us what ceramic structures are, but they do have some things in common, and that is that they are compound materials that contain phases that may be metallic or non-metallic. And ceramics can either be crystalline or amorphous. So what do I mean by crystalline or amorphous? Well, crystalline structures are repeating structures. They follow a set pattern. Amorphous structures, with that A in front, should give you the clue that amorphous structures have no shape or no repeating pattern. So ceramics is what we're talking about. They can be compound materials that contain phases that can be metallic. So they're compound. They can contain metallic substances or non-metallic, and that's probably the best definition we're going to come up with at the moment. Their structure is not clear. It can be either crystalline or amorphous. So really what they are not is they are not polymers with long chains, and they are not metals with that repeating structure. And they basically form their own category called ceramics. Now, naturally occurring ceramics, as I showed you just before, can come in the form of rocks. That's the most popular form. Remember, we're applying all this, the properties and structures, to building materials for civil structures. So this is what's called a sedimentary rock, and it's basically made up of lots of sediments. It's sandstone. Sydney's full of it. And you can see the layers in different colours, and looking in there you can almost probably see some little sparkles going on. Those sparkles are small bits of quartz or inside there, together with silicates, sands. The colour comes from metal oxides. Usually the dark red means an iron oxide. So there's your combination of ceramic material combined using different types of materials, pushed, in this case sedimentary rocks, pushed together under pressure over time. So sedimentary rocks can also contain organic material, so that means things like broken up shells, and they're soft, they're quite easily worked, and they can be used in lots and lots of building applications. The other feature about these sedimentary rocks is that they're fairly porous because they're not very dense, and you can almost scratch it and you can see bits of metal or bits of a rock coming off into my paper here. Water can soak through them. They're quite porous, and sometimes they've even been used as water filters, sedimentary rocks. Okay, other naturally occurring rocks that have been used in building structures. So I've talked about sedimentary rocks, so these will be naturally occurring ceramics. We've got sedimentary rocks. We're going to also look at igneous rocks now. Igneous rocks really form as a result of volcanic action. So water or magma or molten rock comes up from the ground through fissures, and it flows, and when it reaches the surface it cools and it forms typical kind of rocks that are very hard and they're very glassy. They've contained a sort of very dense structure, and this would be an example of an igneous rock. And although you can't quite see it, when I turn it around in a minute we'll discuss it a bit further. It's actually a paperweight, and it's an agate crystal. So you can see the outer edges of the rock here, different kind of substance to the inner edges, and very hot. It's cooled down, it's created this very dense sort of phase, which is very non-porous, so it doesn't absorb any water at all, and inside here you've got some crystalline structures. So this is a good combination of amorphous structures, that glassy phase at the top over here, the very dense crystal structures that are growing in towards the centre, and there's a hollow right in the middle here, which probably allowed this structure to cool inwards, drawing it inwards, meaning that it's created this unique kind of unusual type of structure. But many rocks aren't like this. But igneous rocks, very dense, produced from lava, cooling lava, and typical uses of those, you get things like obsidian, bluestone, or basalt, and they're very often used in the building industry. Very hard to shape, very difficult to shape, unlike sedimentary rocks, but they are very hard wearing, so they're great for use in road and hard wearing surfaces like road bases. They're also used extensively in things like building structures, but again, difficult to work. Now, they, depending on the length, on the speed of cooling, will depend on the type of rock that you have. So a fast cooling rock, a little bit like metals and heat treatment, will produce a very hard, very dense structure. Slower cooling won't be quite as difficult to work with. And lastly, we have metamorphic rocks. So rocks which are changed. So metamorphos, meta meaning across, and morphos meaning to change in Greek. Metamorphic rocks are rocks that have changed their state. So they've been igneous or sedimentary, and through heat and pressure they have become different types of rocks. And a good examples of those would be shale, which is a naturally occurring rock. Under heat and pressure will become slate, which is used extensively because of its layering capacity as roof in the old days, as roof tiles or as flooring. Limestone, which is a naturally occurring stone made up of organic materials, lots of little dead creatures. Under heat and pressure, limestone, which is quite soft, will become marble, which you probably know from lots of bench tops now that are used in kitchens. Very non-porous, very hard, and can be polished. And sandstone, which I just showed you before, under heat and pressure can metamorphose into limestone. Sorry, not into limestone, that's silly for me to say that. Sandstone can metamorphose into quartz. That's it at the end. Okay. And coal with enough pressure can metamorphose into anthracite. Alright, so they're the three main types of rocks, naturally occurring ceramics, and their uses in building structures are considerable. So I'll bring you here to something to show you very quickly now. This is a book called The Builders, National Geographic, and books still come in handy. And here's an ancient road, a little bit hard for you to see in that kind of light, but anyway, there it is, an ancient road paved with probably a granite type of rock that's endured and weathered very well. And that road dates back from around 2,000 years. Okay, other sorts of structures that have been used. We can see bridges. An example here of a beautiful looking bridge with an extended arch made in China at about 650 AD. So again, the use of stone with its strong compressive strength has been, and its plentiful abundance occurring around the earth and around most countries. Its use in civil structures has been structures that do need to be permanent and long wearing, at the same time have firm foundations and can take the weight, and also structures which are designed so as to put the stone in compression rather than in tension, because the stone is very weak in tension. And below here you can see another ancient style of bridge with arches, again where all the members of the structure are in compression. You know, further along you can see medieval towns like England. This is London. Sorry about that glare, but London back in the 1500s, well no, this is actually medieval London. Stone bridges with arches in compression using ceramic stone. Alright, a little bit further on here, now you're looking at the Leaning Tower of Pisa, and Pisa, built in the Middle Ages. This tower here again starting to lean. Why is it leaning? Because stone is so heavy, it's so dense, and in order to create a tower, a high structure, the stone has to be very carefully managed so that it's always in compression, and that the thrust line of force ends up in the middle, not to one side. And this is what's happening here. The foundations have been insecure, they've moved slightly, the thrust line of force is now moving towards the edge of the building, and the building begins to lean. So that's one of the big issues of dealing with stone. Other sorts of ceramics that we spoke about, this one not particularly so much, but over here, this is the Crystal Palace, or a view or artist's impression of the Crystal Palace, built in London. Use of steel to create these tension structures, and glass as a ceramic, used for its optical properties. Not so much in tension, but again in compression, just using its own weight, not even a structural member. The glass allowing light, and that use of glass has been incredibly useful for humanity for thousands of years. Glass making processes have changed, which are now enable it to be used as a plate form, and that meant that it could be used for large structures like that, provided it wasn't a structural member. Here the structural members are steel, or in this case wrought iron, in back here. Okay, and moving on further into other uses of stone or ceramics historically, again heavy, large, solid, long-wearing structures. The Great Wall of China you'll recognise, I'm sure. Further on a little bit, we'll move across onto, again, the Romans. The Romans were brilliant people in lots of ways, engineers. This building that you can see over here is called the Pantheon. And the Pantheon was built around 200 AD, and the Romans had a use of concrete, and they were able to mix up some naturally occurring materials, volcanic materials, and combine them together with some heat and create a cement which could be used as a form of compression mouldable stone. Unreinforced, but still a mouldable stone, and that's how they built such magnificent buildings as this Pantheon that you can see. Again, still using the arch, which is a dome, basically a three-dimensional arch, and not any kind of tension involved here, all compressive members, and stone and ceramics have been used for that. Another further development of that in medieval Europe was the use of the stone to make cathedrals, and the Gothic arch, which is this parabolic kind of shape over here, meant that force could be greater openings, and the force travels in a parabolic shape, creating light. And the use of glass inside these windows meant that the structures, typically heavy stone structures with small openings, because we didn't have tension members to support any of the forces in between those openings, they were eliminated to a degree with these arches. And these Gothic pointed arches enable larger spaces. Stone was used, still in compression, but light was allowed to enter into the building, and you can see that the building changes considerably because the buildings are lighter. With all these empty spaces, they can also be taller, and you can see the use of stained glass here, and I'll show you the roof structure. So again, the roof structure of one of these great cathedrals has a vaulted ceiling, which essentially are arches, and all the arches place everything in compression, and stone could be used to create these very tall, seemingly slender buildings. Difficulty was, of course, that the walls became, with the large walls, required support from the outside, and the support came in the form of these things called flying buttresses, which basically effectively created a very thick wall, but had lots of hollows in between the wall, and created by these arches. So, you can see the construction of the cathedral over here. Again, all stone arches, everything in compression. The walls extended out with these things called naves, so that the pressure on the ceiling pushing outward on the wall will be resisted by these naves, and these other arches transferring the force further away from the wall and allowing the structure to have a bigger footprint, yet not weigh so much that it would crush into the ground. Okay, enough of the historical uses of ceramics. Let's get back into us. Now, I'm going to close it off here. It's about 15 minutes we've been talking for, and I'll go part 2 very, very soon.